This is a concave mirror. It's the exact same concave mirror as last time. So it's exact same concave mirror as question or example 1. All right, so that again, the concave mirror is the one where it's the inside of a spoon. So you're looking on the inside of it. It caves in, if you will. I know it doesn't look curved, but it's just easier to draw the ray diagrams when you don't curve that. So the radius is 3 meters. Again, it's a radius because this is part of a sphere, and so the radius goes from the center out to the edge of the sphere, so that's 3 meters. The focal length, which is a lowercase f, is from the mirror to the focal point. I have these in meters. You can be in meters, you can be in centimeters. As long as all the distances on the principal axis are in the same units, you're fine. Notice that I intentionally made the object height 7 centimeters just to point out that the heights can be in a different unit. The heights can be in a different unit from all of the distances that are measured on the principal axis. So this arrow right here represents the object. So we have some object that is 7 centimeters tall, and it is located 0.9 meters from in front of the mirror. Notice that it is closer to the mirror than the focal point. This is any type of magnifying mirror. Anytime you're like a makeup mirror, when you look at something and you see your face not upside down, you see it all magnified in its wonderful glory, larger than the actual object. Okay, whatever. Makeup mirror is a great example. Again, it's the same mirror as the last one. And the last one, we just had the same object out here in example 1, and the image was right here. It was smaller than the object, inverted, real. This one we're going to get, whenever you're closer to the mirror than the focal point, we're just taking the object and moved it in closer to the mirror. We're going to end up getting a virtual, upright, larger image. Again, this type of mirror is the only one that produces a larger image, magnified. Okay, so we're going to draw the first ray. We always draw the same first ray, parallel to the principal axis. Parallel to this principal axis is the one in black. Go from the top of the object into the mirror. This is a ray, so put an arrow on it. And then it reflects through the focal point. Again, how do I know it reflects through the focal point? Because that's the definition of the focal point. The focal point is defined as rays that are parallel to the principal axis. Any rays parallel to the principal axis will reflect, obeying the law of reflection, through this common point that we call the focal point. All right, so we have one. You could go from, I'll draw this one too. Remember, the second ray went from the top of the object through the focal point and reflects back parallel. What's weird on this case is that the focal point's behind it. And so the light starts from the top of the object and goes to the mirror, but I lined up my ruler with the focal point on the top of the object. That second ray is the exact same second ray I did before. It's just that the light ray doesn't pass through the focal point because the object's already closer to the mirror. But you still line up your ruler with the focal point, top of the object. Go to the mirror, and it reflects back parallel. So this is ray number 2. It's going to reflect back parallel. Okay, so I could draw a third ray just like before. Line up with the center and the top of the object, and then it comes right back on itself. I'll do that as a check in a moment. Notice that these two reflected rays are going away from each other. They're going away from each other, which means they'll never meet, so you can never get a real image. There's no place you could place a piece of paper to get a focused image, because you only get that when the reflected rays converge. They'll never ever converge to a point, never, obviously. And so we go behind the mirror. Well, nothing goes behind the mirror, all right? The light's going to the left. It's going that way. It's not going that way. So that's why it's virtual. We draw these things, the reflected rays, because we're talking about reflection, we're talking about mirrors. Draw the reflected rays backwards and find out where they meet. So that's where they meet. This is your image. So your image is huge. It's way back here. So that's HI. This is DI. They're behind the mirror, so we represent them with negative values. I have drawn this one to scale here, so that I come up with about 21 centimeters. We'll do this mathematically to see how I did. It's positive because it's upright, it doesn't flip over. And then let's check this out. That's kind of interesting. This is about, coincidentally, this is about negative 21. That's just completely coincidental. This is about negative 21 DI, right? Negative 21 centimeters. Those two numbers being the same again, it's just coincidental. This is negative because the image distance is behind the mirror. This is positive because it's pointed upright, just like that arrow's pointed up. Just again, as a check of my ray diagrams, let's see if the one through the center and the top of the object meets at the right spot. Center, top of object. Not bad. So that one goes that way and then back that way, right back in on itself. Okay. Again, that red arrow is just a check. Okay, let's do this mathematically and see how I did. I've already calculated it. Let me grab my piece of paper. According to this, my numbers are off a little bit. Oh, that's not 21 centimeters. Excuse me. That would be 2.1 meters. I forgot I drew this to scale, a scale of 10 centimeters for 1 meter. So that would actually represent 2.1 meters. This. Just because I drew it to scale. And you don't need to draw it to scale. You just have to be able to sketch it and then solve it mathematically. So let's find DI. So 1 over F equals 1 over DO plus 1 over DI. When I solve for 1 over DI, it's going to equal 1 over F, which is 1 over 1.5, minus, I subtract that to the other side, so minus 1 over DO, that's 1 over 0.9, and that value comes out to be negative 0.44. Remember, that's not the answer because that's 1 over DI. I don't want 1 over DI, I actually want DI, and so take the reciprocal of that to get DI. And that came out to be negative 2.25, negative 2.25 meters. Okay, not bad. I had in my sketch here, I had measured negative 2.1. This is the actual value right here. All right. To calculate the magnification, remember that the equation is negative DI over DO. The negative sign is part of the equation. We have two negatives. So we have negative, that's that one, and then the value for DI is negative 2.25. And then all over DO, which I said was 0.9. And that comes out to be 2.5, a positive 2.5 times. So the image is going to be 2.5 times larger than the object. Again, negative times a negative gives you a positive. So this negative sign here tells us that it's virtual. I know we have a virtual image because I have a negative image distance. I also know that all positive magnifications are virtual. And also the positive magnification tells me that it doesn't flip over. All right? So it's upright, virtual, upright, larger. All right? It's upright. It does not flip over. And it's larger because that's larger than 1. So the last part is to solve for HI. So M equals HI over HO. Notice there's no negative sign in the equation when you write it that way. So this is 2.5 equals HI divided by 7, because I said that the object size was 7. And multiply 7 to the other side. So 7 times 2.5, and I get HI equal to 17.5 centimeters is what I have. Okay? Which, that didn't come out so hot. But this is the actual size right there. Okay? And because it's positive, it's because this is pointed upright, you know it's a virtual upright image. Okay?